Can see something. Yeah, okay, good. Record me. Okay, fine.
Yeah, okay, Darek. So please feel free to start your
Fine.
presentation.
So can you hear anything, see anything? I hope so.
Yes.
Yeah.
Yes.
Fine. So what I will show here is just an extension of what I've been showing on the seminar, and it's more of a nice presentation and less of some hard math and hard calculations, because although the math itself, well, you will see it's not that complicated, because we can just do with essentially high school math and some basic algebraic and calculus things. It's just not complicated because of some complicated apparatus, but just because of the ugly mappings that we need to handle. So I will try to concentrate more on the nice stuff, on the pictures, animations, and so on. And of course, it should be said that this is work that I am doing along with Professor Tis, who is my supervisor. So essentially, the division of the work goes like this. He made all the nice pictures and animations, and he also got the idea of just experimenting with the system that I will show you. And I just try to explain whatever I can, and I have had some success, so that's what I will try to show you. I will do it roughly in 3 parts. First, I will show off the problem and the system that we are experimenting with. Then I will just show some animations to give you some better idea of what's happening in there, and then a couple of exact calculations. And maybe at the end, I will be able to show off something that I'm working on right now, and perhaps some of you will be even able to help me with it, because I seem to be not exactly stuck, but it's getting quite ugly and I could use some help. So maybe it will get to that. So let's start. The title of the talk is a billiard on some hemisphere. So it would be nice to say what a billiard is. And it's just a, quote, simple system in which one particle travels only in straight lines, or geodesics if it's non-flat, and bounces off some obstacles that we put in there. And the bouncing is always perfect, so it just reflects according to the usual law of reflection, that the incoming and outgoing angle are the same. So we could write this as some kind of Hamiltonian system, where the Hamiltonian would be 1/2 here. Just this, you can substitute with this with some other notion of the metric if you don't have flat setting, and then just some potential, which is either 0 or plus infinite. So it's just a peculiarly shaped infinite potential well. And so the problem seems to be quite simple. However, it's not that simple, because according to the shape that we give the billiard, it can do very weird things. So for instance, if we take 2 straight lines like this and close it off with a semicircle on each side, then we get something that is called a Bunimovic stadium, if I can spell it correctly. And if we put a particle in here and just let it bounce, then we are going to get some pretty chaotic movement. And let's just use a nice YouTube video of that. Yeah, nice. So let's skip this. Okay, hopefully you will be able to see this as well. So here we started with a circular wavefront and just let it bounce around, and you will see that the movement is pretty chaotic. After some time, essentially each of the particles will just have totally forgotten about where it came from, and it will just be going around with some probability distribution. So as we will see, this thing is actually so-called an ergodic system, which means that if we wait for some long time, then the particle will just go through all the possible configurations of position and velocity direction. So essentially speaking, we can just substitute time averages for some probability distribution of the velocities and the positions. And here you can see that it just got somehow diluted and all the particles are just swimming around without much system to it. And if we wait for a little bit more, then just the particles will have filled it pretty much completely.
I guess technically speaking, it's a dense subset.
Yeah. So there is nothing really nice here. So as you have seen, this kind of system can be actually quite complicated, and the ergodicity is actually a thing that is quite often studied in those billiards because it has some nice applications, especially to the statistical mechanics, because in statistical mechanics, we just sort of assume that all the systems are ergodic and we just don't, excuse me, we just don't care about the rest or some technical proofs. But these billiards and this system can give us a way to at least try to prove the ergodicity for some simple toy models of statistical mechanics. So another system would be so-called Sinai, my spelling, billiard, and that is obtained by taking one fixed disk and letting one point particle bounce around. And furthermore, we put it on a two-dimensional torus, so when the particle comes off in this direction, it will come in from the other side. And the same thing works for the other direction as well. And this can simulate one particle bouncing inside a grid of hard spheres. And of course, it can also simulate one hard sphere bouncing around in a grid of hard spheres, because if the sphere that is bouncing here has some non-zero radius, we just can enlarge the radiuses of all the other spheres by that amount. And of course, this thing also is ergodic, so that is some nice result that has direct application to statistical mechanics, in that sense that our assumptions about that ergodicity are not wrong. But this was just to give it some more background. In fact, we are not really caring about the ergodicity of our system. As we will see, it is not ergodic at all. And we are just trying to explain whatever we can. We also don't have any kind of obstacles in there. We just have some peculiarly shaped thing on which the particle circles around. So here is the surface on which the particle is running around, and it's just a spherical sector. So here you have a view from 3 different sides. As you can see, it has just a spherical back. And from the top, it also just looks like a V-shaped part of a sphere with some angle in here that we will call capital phi. And on the other side, it is surrounded by the 2 half disks, this one and this one. And the only thing we are trying to do here is just tracing the path of the particle. And since we are not really assuming any other forces, then the particle is just moving in geodesics. So here on the disks or parts of the disk, it's just straight lines. And on the sphere, it's great circles. So that sounds really simple, right? But before we show something more, we should really make some order in our notations. So I've already denoted the sector angle by capital phi in here. But since, as the title of the talk already suggests, we are trying to explain mostly almost hemispherical surfaces. So we put phi equals pi minus epsilon, where epsilon is something positive but quite small. And now we can introduce some coordinates on it. So first of all, we take the 2 halves of the disk and treat it just like one disk, because it's nothing more than a disk that has been slightly bent here. I can't hit it, but here through this line. And a nice consequence of this fact is that if we remove that bend, then the particle will just go in straight lines on the disk. So here, if we send it in the direction of the arrow, then it just goes here in the straight line. And then it comes around on the spherical part. So this is probably the best way we can describe it. And we use 2 angles on the disk, theta and omega, where the theta is giving the position of the particle as it enters the disk. We are not caring about the particle anywhere else. We just have the particle somewhere on the edge of the disk. Then we do one step, which means that the particle runs on the disk and then on the spherical part, and then it will emerge somewhere else on the edge of the disk. And that was one step of, let's say, our mapping that we will try to study. So these 2 numbers, or 3, are the only thing that we are caring about. This theta, which just will show the position of the particle as it is entering the disk, and the omega that shows the direction of the particle. And we measure it with respect to this radius of the circle. So the omega is positive when it goes to the right from the radius. And finally, we have this sigma here, and that's more or less just a technical thing. Instead of the theta being from minus pi to plus pi, it's just nicer if we divide it into 2 things, a theta that goes from 0 to pi, and the sigma that just holds the sign. So it's plus or minus 1. And this is nicer just from some technical points of view, So that's the only reason we are really caring about this sigma. So the theta is positive on both sides. Here it would be also positive, but the sigma is different. And now when we have got through all of the notations, we can actually start showing off some images. If we just pick a point on the edge of the disk and let the particle run around for some time, then we get images like this. Here in the plane, we have omega on the horizontal axis and theta on the vertical. And each time the particle comes to the edge of the disk, we just make one point in this picture. And as it is going around, we add more points. And when the particle, and it's important to say that all of those points are the same color. So one initial condition means one color. If the colors are different on the image, then it means that the initial conditions to get into that point were different. So that's the meaning of the color. It differentiates the various initial conditions that we gave to the particle. Another thing to mention is that, as you can see, there are many holes in the image like these. And that does not mean that there's not anything in there. It just means that we couldn't hit that particular spot with our initial conditions. So we just didn't put any points in there when we were, or Professor Tis was calculating the image. But of course, that doesn't mean that there is not anything in there. And it would be maybe nicer if I could show it in some more detail. Yes. So as you can see in here, most of the image, which is for epsilon 0.02, so the angle is not that small already. This is for 0.02. We get some nice stacks of ellipses here. And for each initial condition, for most of them, we get quite nice ellipses. Because as you can see, all those ellipses have similar colors if they are like in one vertical column. We can see that the particle is just jumping around those ellipses. So if it started, for instance, somewhere in here, I hope you can see the mouse cursor, then it will just jump here, then here, then here, and then return to the top stack. And along with that, it will rotate around the center of the stack. So that's how the system mostly works. But I say mostly because it's not what I wanted. There are also chaotic parts in this system. So if we shoot the particle in some particular direction and with some particular velocity, we actually get chaotic behavior. And if you look at the image here, you can get a good idea about such a chaotic behavior. If you look at the right-hand side, you will just see those gray points pretty much everywhere. And that means that if we just start the particle here on the top of the disk and send it straight down, then it will result in such a chaotic motion. However, and now I can just play the animation, but first of all, it would be nice to say that, as you can see, here are some colorful lines on the disk, and there are appropriate colored points in the plane that you maybe can't see, but if you have any trouble seeing this, you can zoom in the zoom settings. There is a setting to zoom if you click on the drop-down menu that says something like Darek is presenting screen or something like that. And you can set the level of zoom in there. So if you can't see it in sufficient detail, then be sure to use that. And these colored lines and points correspond to first couple of steps of the mapping. So we start in here and we go along the red line here, straight down. Okay, and then we just go around on the sphere and then we emerge somewhere else. And in that way, we make the first couple of lines. And the rest of gray lines and gray points is just whatever came after that. So only the first couple of iterations are differentiated by the color and the rest is just gray. And here, when we've explained this, we can just play the animation and you will see how the regimes of the behavior change when we just move the initial condition along the top edge of the disk. So after some chaotic mess, we get kind of regular behavior here. As you can see, we get, well, let's go a bit back, some quite regular thing here on the disk and a little stack of ellipses here in the plane. And those ellipses are growing and the figure on the left is just getting more blurred. And when the ellipses kind of hit one another, then actually the regular regime stops and it breaks off into some chaos, as you could see in here. Let me return. Here the thing is that in between those three kind of ellipses, there are three more that we didn't hit with that initial condition. So here the chaos occurs when the ellipse that we can see hits one of those that we cannot see. And here it breaks into some more chaos and it emerges into some more regular behavior. This is the stack of the four ellipses that we could see on the image. And it gets more blurred until the ellipses touch and then it breaks off once again. So this is something that is quite characteristic of this system, this alternation of regular and chaotic regimes. And it's something that we can't see in the classical billiards, let's say. If you remember the Dunimovich Stadium, well, it was just totally chaotic. If we started anywhere we wanted, we would just get, I'm sorry, we would just get some chaos after some time. And of course, when the system is ergodic, it works like this, no matter where we start, because after some time, the particle just needs to have forgotten from where it came, and it just needs to go through all the positions and velocities with some probabilities that can be calculated. So this is how our system differs from the classical billiard. So it's actually not that much connected to the, let's say, classical theory of billiards. Yeah. And there is one more thing that I wanted to show you. And this is this one. Here you will see how the behavior changes when we change the sector angle, if we change this phi. And since this animation is quite old, then it's, first of all, it's rotated. So there is theta on the horizontal and omega on the vertical. So it's just rotated 90 degrees and flipped. And it goes from phi equals 0 to phi equals pi. So this is essentially non-existent part, non-existent sector. It just two parts of the disk very close together with some little angle here. And it goes progressively towards the hemisphere. So just something like this. And the color key is the same. The same color means that the points came from the same initial condition. And now we will see how it works. And please beware, if you, for any reason, don't like flashy or mesmerizing videos, then please don't look at it. But if you are prepared, then let's start. Here it just breaks into some total chaos. This is still quite small, phi. And there it's mostly chaos with some little islands of regular regimes. Of course, those holes will contain something similar. Once more, we just didn't hit them with our initial conditions. This was quite nice because in some sense, those regular islands just grow and touch, and then they merge one with another. This is something like 2 pi over 3. And only now, when we are at the very end of the video, we get the behavior that we are trying to study, which means for angles that are nearly pi, or pi minus some small epsilon. And you can also see all the stacks of ellipses here. They are just squashed in some way because we are viewing it in some differently scaled coordinates, but it's there. So this is how it behaves when we change the sector angle. And you can once more see that there are very nice, or well, nice, very interesting alternations between regular behavior and chaotic regimes. And that's what the system really does and what makes it in some way special. So that were the animations, and now we could just go through some math. As you can remember, there were some nice stacks of ellipses in here. And I was actually able to explain some of them, at least this large. I'm sorry, this is not what I wanted. Go back. Okay. So let's try again. I'm sorry, I just skimmed past the image. I was at least able to explain these large ellipses and this stack of 4. Or to be more precise, I've just explained the top stack out of all of those. Yeah, here it is. However, the method that I used can be in principle used for all the other stacks. However, it will get progressively more messy. So this is something I didn't even try to do. But first of all, we need to write down some equations for the motion of the particle, and we just write down the equations for the straight lines on the disk, and that looks like this. And I won't be going through that anymore, but I just want to show it because it will be nice if you will have some idea about well, the ugliness of all those equations. Here on the disk, it's pretty simple, but the spherical part is much worse because we need to first make a plane through the center of the sphere, which will describe the great circle on the surface of the sphere. And it gets quite messy. And these calculations are what Professor Tis did in order to make all of those pictures and simulations. And as you can see, they are really not that nice because in these two equations, we have some more variables that come from the parameters of the plane that we need to use for the great circle. And all in all, the relationship is quite complicated, especially with this ugly square root in here. So in order to be able to iterate this mapping, and let's just show it in some better way. This is some, let's say, disk part, and this is the sphere part. Then we need to do sphere after the disk, and that is one step of the mapping. So if we want to make more steps, we of course need to make some power of this expression, and as you can see, it will get ugly quite fast. So we need to use some more trickery to make it more manageable. First of all, we will show that the squares of those A's, B's, and C's add up to 1, which is really simple to show. And it's so simple that I can do it right here. If you look at those two, A prime and B prime, and take squares, then it's quite obvious that the middle part will just subtract. So if we do that, okay, I can't fit it in here, but b squared sigma squared, since sigma is only plus or minus 1, I can just drop that, sigma squared, and here's the sign, and in here we have b squared cosine squared minus this whole thing, and plus a squared sine squared. So the middle part will just subtract, and a prime squared plus b prime squared will just be a squared plus b squared. And if you look at those equations, you will see that they are just a little bit modified equations for the spherical coordinates. So if we just square them and add up, then we need to get a 1. So that's one thing that will be quite useful with simplifying those expressions. But first of all, let's get rid of this ugly square root. And one nice thing is that we can use this kind of formula to re-express the cosine in terms of cotangents. So if we keep the cosine here, we will get an ugly formula with an ugly square root. But if we just exchange that for a cotangent, then we can get something that is a lot nicer. So if we do that, we see that the cotangent needs to be minus a prime over c, and it gives this kind of equation, which is still not really nice, but it's a lot better than the ugly square root. And when we want to make our second equation for the omega, we can use to great effect this normalization condition that says that those a's, b's, and c's add up to 1 if we square them. Because if we square the sign here, we just get the b prime squared, and we can just substitute that with all the other squares subtracted from 1. And after some easy manipulations, we actually can bring it down to the form that contains the cotangent that we obtained in here. So after some more work, we just find that there is this kind of law of sines at work for all of those parameters, which is quite nice, and it will make it very easy, or reasonably easy, to make some approximations later. So these two tricks are quite important for our success. Yeah. But before I will continue with that, I will want to make a little detour, because those two equations have some nice properties that we in the end didn't use, but they are at least nice. So let's show them off when we have the time to do that. When we multiply this by the sine of 2 omega minus theta, then we get this equation, and it's quite important because in spherical triangles, in the spherical geometry, there is a very, very similar formula for the spherical triangles, and it looks like this. And now you can see that we can just assign the sides and angles of the spherical triangle to some of those parameters of our problem, and it will give the correct formula. So yeah, oh, let's get to this table later. But if we take the law of sines that we derived before, we can also write it in the form of a real, let's say, law of sines. So it has all sines in here. And once more, a very similar law of sines holds for the spherical triangles as well. So that's a nice thing too. And because of those two equations, we actually managed, or I managed, to just assign the parameters of the problem to the sides and angles of the spherical triangle. And then the problem could be actually solved by just chaining the spherical triangles. So I just put a handwritten table in here because that's what we were using. And in the end, it just well, we saw that the spherical triangles in fact don't add anything that would be worth the trouble of keeping them around. So we just discarded them in the end. But I at least think that it's nice to show such kind of relationship. So I wanted to at least mention them. And as you can see here, two of the sides will perfectly match together. So if we keep on one side of the disk without any jumping at all, then we can just chain those triangles in such a way that we put one side right next to the other. So here it would be the side A for one triangle, and here the side B for the same triangle. But since the side A for the next triangle in sequence, for the next step, is in exactly the same form, then we can also say that this is the side A in the next triangle. So those triangles can be chained in this nice way. However, we need to keep more types of those triangles around because they are different according to the sign of sine 2 omega minus theta. Because when we jump, oh, well, let's not return here and let's show it in here. If we jump through the center from top to bottom, then actually quite a lot of sign change, and we need to take care of that by keeping two separate triangles and chaining them in the appropriate fashion. And we will also see that this is a huge problem for us in the other computations as well, because it just means that we need to know beforehand how to chain those steps with jumps over the center line and how to chain them with those steps that don't have the jump, which is quite ugly because we can find out how it is for the nice stacks of ellipses, but in the chaotic case, it's quite impossible to say how they will just go one after the other, because if we are trying to just chain the mappings in some nice way and try to repeat a sequence, for instance, of one that jumps and then, I don't know, let's say two that don't jump, then we can only explain those stacks of ellipses, but never the chaotic regime. So that's something that is quite nasty of this problem. And here is also one picture that I wanted to show to of the spherical triangles. Here you can see how they really nicely chain together, and the parameters of the problem, so the omegas and thetas, or I think it's 2 omega minus theta, can be read from those spherical triangles by looking at those sides, those long sides from the pole to the actual curve in here, and this angle here. Well, if I could. And as we chain the triangles and make more and more steps of the mapping, we can just read the appropriate parameters from this one side and one angle. However, as I said, they weren't that useful, and in the end, we just dropped them because they were making more trouble than they were worth of. So now let's show, at least in some simple way, how we could explain the large stack of ellipses. This one. Before we do that, we will do well if we linearize the relations that we got from those manipulations that we did earlier. So I mean, these two equations. And the only thing we did with them is just linearize with respect to epsilon. So we just put the phi equals pi minus epsilon and assume that epsilon is small enough that we can just write it up to the first order of epsilon and throw out the rest. So when we linearize this one, we get such a nice relationship for the new theta and the old parameters. And when we have this, we can use the law of sines, so-called, to obtain this kind of linearization for the omega. And it's not really hard, but you could see this, for instance, by realizing that the cotangent of x plus some h is cotangent x minus 1 over sine squared x times h. So if we compare this Taylor series essentially with this equation, we find that the theta needs to be like this. And when we know how the new theta has to look like, then we can use this law of sines to get the new omega, because the new theta is right here in this sign. But when we know already what the theta is, then we have no problem linearizing. So in this way, we obtained these much simplified relations for small epsilon. And from those relations, we can actually explain those stacks of ellipses. So let's do that. I won't be doing it in much detail, but at least you will get some rough idea. Essentially, the method is always the same. We somehow guess where the center of the stack is. And here it's not hard. It's just in theta equals pi over 2 and omega equals 0. So the only thing we need to do is that we just use new variables that go around this center. And now we also suppose that the difference between the center and the actual point is only small. And there were a couple of plus or minuses that refer only to the sign of the 2 omega minus theta. And this sign relates to the fact that we jump or not jump over the center line. And here, since the ellipse is on one side of the center line, then we don't jump at all. And so we can just choose the minus sign for the plus or minus, which means that we don't jump. And after we just do this and linearize by just substituting the arguments for sines and tangents, just saying that the cosine is equal to 1, we get a nice linear recurrence relation that looks like this. And now we can just solve it by the usual means, which means that we first calculate the eigenvalues that need to satisfy this equation. And we are doing everything only up to the first order of epsilon. So here in the determinant, for instance, we just neglect the epsilon squared, and in the first order, these two cancel. So the determinant is just 1, and it goes in here. And the trace 2 minus 2 epsilon goes in here, and I have missed a lambda in here, so that is a typo, but the lambda should be in here. And now if we just solve this in the elementary fashion, then we get this very nice result up to the first order. And if we convert that into the polar coordinates of the complex numbers, then we see that up to the first order, again, it has unit magnitude, and the argument is some constant. So actually, these eigenvalues can be written just like a simple complex exponential like this. And as we know, then the solution will just look something like this. We will have theta. Well, let's not write this. We will just write P and Q. And here we get some constant times lambda 1 to the nth power plus b and here will be the second eigenvalue to the nth power, and similar stuff for the q. So if the eigenvalue is equal to just this complex exponential, it actually means that the solution will be kind of periodic. And this is exactly what we have seen in the images. And since each step actually adds the angle of square root of 2 epsilon, then we just can expect then the particle will go around the ellipse after 2 pi over the square root steps. And this is something that was in excellent agreement with the numerical calculations. And I can also show you how that ended up, but only if I can find it. Looks like, yeah, here it is. So this is a little table that Professor Tis made back when we were explaining those large ellipses, with various parameters of those ellipses that he got by just, let's say, making the program look at the ellipses and calculate the parameters. Here in the first column, we have the epsilon in radians, of course. And here are some parameters of the ellipse. And one parameter in particular that we are interested in is this column, because this shows precisely this angle that is between each two neighboring points on the ellipse. And of course, this angle, as I said it, is not any real angle, because it's somehow squashed in the process of parametrizing the ellipse. But it is kind of an angle that measures after how many steps we go around. And here you can see that it really is sort of square root of 2 epsilon, exactly as we showed before. So one nice example is this row, for instance. Nice. Here we have the epsilon equal to 10 to the minus 4. And here you can clearly see the usual decimal value square root of 2. So this is really, and here we have 2 times 10 to the minus 4. And if we multiply that by 2, we get 4 times 2 to the minus 4. And we see that we have just 0.02, so, or 2 times 10 to the minus 2, which is very precisely exactly the square root that we calculated here. So in fact, this is really a good result, which relates quite well to the numerical computations. And one full go around is completed in this many steps. And of course, we can also just carry on with the standard routine and get some real solution of the recurrence relation. And it looks like this. So we can see that it precisely gives some ellipse. After we just divide by the square root and square and add, we get this equation of ellipse. And this is also in very nice agreement with what we calculated. One thing that is nice is, for instance, the tilt of those ellipses. If you look closely, you will see that, well, it's quite hard to see, but those ellipses are not like in the normal position. So they are not like this, but they are actually tilted by some angle. So they look more like this. If you look carefully, you will see that, I think. And this tilt can be simply calculated from these coefficients, and it also gives a very nice result because the tilt in the table, I think, yeah, it's this column. It just gives half of that epsilon, and if we calculated it, we would get something like tangent of 2 times of that angle is equal, and now I think it's this coefficient, which is -2, over this coefficient, which is 1, minus this one. So here you can see that those ones cancel, and those 2's and minuses cancel as well. So if we just say that the tangent is approximately equal to its argument, then we precisely get this nice result for the tilt. And you can see once more that in this column that shows the tilt, we get pretty much exactly 1/2 of the value that we get for the epsilon. So this is really a nice result that is in great agreement with what we were able to calculate. So this is really a nice thing. And so in the similar spirit, I try to do this stack of 4. And essentially the method is the same. It just, everything is far more messy, but the idea is just the same. And the biggest difference is that we need to take care about that point jumping around, because in this image, it jumps like this. And while jumping from one of those stacks to the next, it will also slowly rotate around the center. So it may be here in the top stack, but if it goes to the next one, it will be, for instance, in here. And in this way, it will slowly rotate. So if I want to get an equation for one of those ellipses or one of those stacks, then I need to chain 4 of those steps together, so that if I start somewhere here on one of those ellipses, then after one step of the map that I'm considering, I will end on the same ellipse as well. So here I will actually need to chain the cases that don't jump, then jump, then don't jump, then jump. And as you saw before, each one of those mappings is given by an equation which is not very nice. And of course, what happens when we need to compose them in this way? And essentially, the process was so painful that I just put it into the computer and didn't even try very much to do it by hand. And after making the computer to do that, we get this monster recurrence relationship. One thing is good to notice here, and that's this -6 pi. If we just return here, we can see that one of those jumps goes like around from the bottom of the image right to the top. And this jump will add, oh, I'm sorry, I wanted to go here. Essentially, this jump will add 2 pi to this angle beta. So this -6 pi is essentially -4 pi that was a result of the composition, and we needed to subtract those 2 pi from going a full circle around. So there's some just a little notice here. And you can also see that the notation is different. Here we have some a's and betas, and these are precisely the angles and sides of the spherical triangles, because I did this with those spherical triangles, but of course, when I just dropped them and went to use just the linearized relations, I just hadn't the guts to go through this and convert it to the new notation. So here we have all those equations still for those old sides A and angles beta. And we are trying to investigate the top of the four stacks. So we have four, one on top of the other, and we are going just to describe the ellipsis in the top one. So we just guess its center, which if you look at the image is sort of correct because this is in the half. So when this goes from 0 to pi over 2, then you have pi over 4 in the half. And of course, if this is pi, then it's reasonable to expect that if we have two such ellipses that will fill the pi, then we just can expect that each of those has kind of vertical axis equal to pi 4, and that will give this approximate position of the center. And so we, after writing down these monstrous relations, we just go through the steps once more. We put in those new variables to just make it centered on the values that we want. And after some more expansions and linearizing, we get this kind of linear recurrence. And I won't even go through the solutions. I will just write it down and you can see it in here. So the first thing that can be saw in here is the thing that after each step, we go by angle equal to this weird value. So each step on one of those ellipses goes through this angle. So after this many steps, we can expect the whole ellipse to be circled around. And once again, this is something that Professor Titz managed to show numerically that this really works. So this is something really nice that we could explain one more stack. And of course, we didn't make any mistake in those monstrous calculations. There is also one peculiar thing. If you, well, it's not really visible at this picture, but all of those ellipses, except for the big stack here, have quite similar ratios of their axes. So actually, when we scale the picture so that those axes are the same, then we get stacks of circles, and those stacks of circles were what we were working with when Professor Titz made the original pictures that were just for our better understanding. But the stack that is here down in the left corner, it's different, and the ratio just differs by some constant. And Professor Titz dubbed it the Bulgarian constant, which is a reference to a joke that we use in the Czech language. But this thing make it possible to show that this magical, mysterious Bulgarian constant is actually equal to the fourth root of 2. So this is also a factor that somehow governs the ratios of those ellipses. in comparison to ratio of those ellipses in the corner. And we don't know why this should be like this. I have no idea. I would even say that this is something that is highly improbable, but the numerical experiments just show that it's quite precisely true. So in this way, we have obtained the equations for this stack of ellipses that is on top in here. And it also works quite nicely when we compare it with the numerical computations. But it's obvious that this process cannot be really brought farther because we need to chain more and more and more of these, and the relations would get just messier and messier. And worst of all, we don't have any real general idea of how these relations could be formed depending on the number of steps. So essentially, for each of those steps, we would need to do a separate calculation using the computer, solve those ugly recurrences, and then get just some random result that is nice and true, but that is hard to bring in line with all the other results, and it's hard to get some general idea out of. So this is something that I don't continue with, and now comes the magical part that I will just cover in a little bit of time because we are already running for more than 1 hour. And this idea is really something crazy. So if you just spot anything that could be made in a better fashion, then please tell me, because this, as I have written it on my papers, it's just ugly and I don't know if it's good for anything. But let's start. Essentially, the idea that I try to pursue now is the one that if we have the linearized, oh, I don't want green, linearized relations that look like this. Oh, it would be perhaps better to just go somewhere here and show it. On these, yeah, these two. Let's just erase the rest of those things. Yeah. So these two relations are not that much complicated, and we could do a trick with some forced linearization that would enable us to make a general power of this mapping. And the idea that I had is this: if we have, I will just if we have this, then what I would like is just taking not only those phi's and omegas, but I would like to add some more things to them and then carry them around as some sort of vector. So this is clearly not linear, and we can't use any matrix M for doing something like this, just because it's not linear. Oh, I mean, however, if we extend those vectors, there is chance that we could be able to get away with it. So for instance, here we need to add epsilon times this tangent and this sine. So what we do is that we just add this product to the things that we are carrying around in the vector. And of course, here we need this cosine. So we need to carry around that cosine as well, and so on and so on. So now, every time when we add something to the vector, we of course need to see how it transforms when we do the mapping. And here, fortunately, if we just say that we go to the first order, then we are very lucky to have all those trigonometric functions only in the product with that epsilon. So essentially, when we try to get, let's say, this cosine after one step of the mapping, then we don't need to expand this at all. We just take the value up to the epsilon to the 0th power, and that's it. So for us, this is just the cosine of, and here it goes, minus plus 2 of omega, because this is the, let's say, main part of the new omega. And here we get this, so we also subtract it. And this is what we want for the new cosine of this linear combination. So we get something like, we can ignore the sign, so we have 4 omega minus theta. And of course, this can be expanded. And in this way, we actually can bring it to such a form that it's, let's say, closed, that we don't need to add any more things, and it just holds together, and all of those things transform only one into another. However, there is a little problem with that, because we can close it in this way, but only when we consider an infinite amount of possibilities. So here, if we try to do, let's say, let me just rummage through the papers. Yeah, here we have what I wanted. So we actually need to carry all the things that look like this. And here we can add the 4. So each multiple of 4 can be here, and we need to carry it somewhere in the vector. And the same thing holds for the product of those two things. And we also need a product that has the tangent in it, because here we have the product with the tangent, so we need to keep that around as well. And we need 2 of them. And when we consider all of those possibilities, then they transform only one into another. And one nice thing is that those, let's say, higher frequencies come into play only when we iterate the mapping too much, let's say, because when we start, this product gets only the functions that have the frequency of 4. And in the next step, it will expand, and the frequencies of 8 will come into play. And on the next step, we will get the 12s and then the 16s and so on. So essentially, if we can limit the number of iterations, and we can, of course, because still because we have that sign in here, and we need to decide beforehand how we will connect the mappings, then we at least know that the iteration has some fixed number of points. So if we go, I don't know, let's draw this stack of 6 ellipses. If we want to explain those, then it's just sufficient to take 6 jumps in here, and we don't need to care about the rest. So at least one, this is one nice thing about this. But all in all, I see several possibilities with this, and they are all very ugly and unfriendly. So one possibility is just an infinite matrix that would be truncated as we have need of. So we would do the infinite matrix, and then we would say that essentially that if we want the 6 jumps only, then we just cut it off at the frequency of 24, and here the others would just be left out. And then we just could take the matrix and calculate the eigenvalues and eigenvectors and so on, and we could essentially do a general power of this truncated matrix. So this is one possible way of doing that. And the other way of doing that would be through generating functions, which I tried really, I was working on that just before I started this seminar. So it's really 1 hour old. We just take some generating function, which will keep the parameters like this, where these omegas and thetas, they are just some variables that serve no other purpose than to keep apart those values that we are interested in. So if we want to get the omega, the value of omega, then we just differentiate with respect to the big omega that keeps it apart from the other things, and all the other things will vanish, and we will just get this omega. So this is the way in which the generating functions work. And of course, we can add things like this for everything that we need. So here we need to add tangent and the cosine. And here we can add the infinite amount of things that we need to carry around in some, well, let's not say nice, but at least useful way, because we can actually get some infinite series in here. Let's say that we would get something like the tangent in here and sine, and then we would get something like cosine for an omega times, and here I would put some power of that variable that serves to keep all the stuff separated. And of course, this infinite series can be summed, and that will give some nice, let's say, closed form for the generating function. And then we will construct a monstrous differential operator, which will be ugly, and I haven't even written it down, that will just do one thing, and it will take the generating function, we do the operator, and we get the generating function one step later. So after this, if we did, for instance, this, we would get the omega after one step. And of course, we could iterate this as we would see fit, but then we have the problem of calculating a general nth power of some monstrous differential operator. So that's something I'm not really sure how to do. If I just should try to mess with the eigenvalues and eigenfunctions, but there is also a problem that there is a good chance that those eigenfunctions won't be even square integrable. So I don't really know what to do with it. So essentially, this is what I try to do now. And if I succeed with this, it will just give some other way of looking at the problem, because we don't solve each of those ellipses in separation, but we just do everything at once. But the problem is that it's very ugly, so I'm not even sure that I can get some good results for it. So if you by chance would have any idea about how to go about this thing, like making a general power of a differential operator that will be linear, that is at least one nice thing about it, then please tell me, or if you have a nice book of this, that would be nice. Essentially, the only thing that I know is that something like this is done in functional analysis, but of course, the only part of functional analysis that I ever had was literally the part of the quantum mechanics course, and there wasn't really much space for that in there. So we just went through all the needed stuff and then went on with the physics. So that's what I'm trying to do. And if you had any idea, I will be grateful. And I think that this is everything I had to say. So if you want, you can ask something, but well, I won't be probably able to answer. So just, you may try if you want.
Okay, thank you very much for the nice and pretty presentation. So yeah, please, anyone, if you want to ask or comment, feel free.
I first have a technical question. The plus minus, was that the sigma? The plus minus that you discussed just last, the last thing before you went into generating functions?
Yeah, the plus or minus, it is just a shorthand for
that one.
For this thing. Well, it's so scribbled over that you maybe can't see it, but the plus or minus is just sine of sine.
Okay, the double
to omega
sign.
minus theta. And this thing is important because it says whether the particle will essentially stay on the same half of the phase space or if it will jump over. So either here over the central line or from the bottom to the top. And the cases where the particle jumps are different to those that don't jump. So we need to carry that around. So that's what the plus or minus is.
Okay. So the other thing I had in mind was maybe a good idea, but I guess you already have that. But a good idea would probably be to look at the simplest chaotic system that would display similar behavior that you can think of. So I mean, I don't know much about the chaotic system, but I think, for instance, already the double periodic, the double pendulum also shows islands of, I mean, order and then chaos in between and so on.
Yeah, that's a nice idea, and we actually haven't done that.
Yeah,
because,
and of course the double pendulum in itself is quite complicated, but it might actually be simpler than your system. So there might be some literature on that can inspire you what to do next. And I just mentioned double pendulum. I think that one of the simplest systems which have chaos in 2D is something called the Henon system, which is a cubic potential. There might be some nice toy model which can inspire you.
Yeah, thanks. Well, to be honest, we didn't try to find, let's say, a toy model for a toy model. So
yeah, sure, but
but it may be well worth the shot. So thank you.
Darek, I have some comments. Maybe it's it's a good idea to look at some simpler system, but well, I think what you actually have, you have a discrete symplectic map, because the map from the Q's and P's to these other Q's and P's, I think it's symplectic.
Yeah, that sounds
You have a
reasonable.
discrete symplectic map. And also this whole situation where you have part of a sphere with a boundary and also a disk which also has boundary. You have to somehow, I think you would have to get rid of the North and South Pole in order for this to work. But you won't ever hit them.
Yes.
Most of the time you won't hit them anyway. So you would just get rid of these poles, and on both of these manifolds, which are just Riemannian manifolds, you have geodesic flows.
Yeah.
The dynamics is really simple: straight lines and great circles, right?
Yes.
But what's difficult is what happens at the boundary. And you have a general theory how to glue together two symplectic manifolds on at the boundary. And you basically have some large symplectic manifold of dimension 4 in this case, because there are two coordinates and two momenta. And from this you get a simpler system which is also symplectic and which works, and it's discrete, which just works between the boundaries. So
yeah.
that's the general theory, and you have a general theory of symplectic gluing. So I don't know much about it. I've had some symplectic geometry like, I don't know, 15 years ago. I forgot most of it, but I remember this. And it's not a billiard, because when you have a billiard, you have just one. You have a manifold with one boundary, and at the boundary you have some reflection map.
Yeah.
This is actually not a stadium. It's gluing of, maybe you can think of it as one symplectic manifold, and you glue together some of its boundaries.
Yeah, I'm only not sure if we actually haven't done that, because we had to write down those two sets of equations that just like take the point from the disk to the sphere and so on. So I'm not sure if the theory that you are describing wouldn't do just the same thing for us.
Yeah, it would, but maybe the difficulty you are facing is just choice of coordinates. You know, sometimes when you write the same thing in different coordinates,
yeah, of
then
course,
it looks simpler. So maybe if you would use coordinates which are adapted to the symplectic structure, which are basically P's and Q's, like momenta and coordinates, then it might be simpler. And also the maps between the maps would be symplectic. So now they might also be symplectic, but not all of them. So that could help, maybe.
Yeah, it would be really nice if we could simplify that further. I tried to just manipulate those equations and see if I couldn't just introduce some coordinate that would behave in a nicer way, but that failed, of course.
Yeah, it's always hard to, well, a problem which is simpler in one set of coordinates might look horribly difficult in a different set of coordinates. And it's extremely hard to find the right coordinates. So that's one
Well,
reason why people like to work with manifolds, because everything you prove holds in all coordinate systems, all possible coordinate systems.
Well,
You can use some other kind of reasoning to pick the right coordinate system, and then it will look simple. So,
no, if the theory could simplify that, that would be, of course, great.
yeah, but
The only problem is that I don't know anything about it.
yeah, if it's worth the effort to learn the theory, yeah, that's of course understandable. And well, I don't even know. I have some handwritten notes from 15 years ago. I could look. I could look at the literature, but well, you can maybe look at some books about chaotic dynamics and focus on Hamiltonian or symplectic systems.
Yeah.
Discrete symplectic mappings or something like that. Maybe Google or look at some such mappings, because I think what you have is an example of this.
That would be nice if this kind of simply work. Thanks for that suggestion. And I even have one book here, which I'm, well, not now, but sometimes. So hopefully it will at least point in the correct direction.
Okay, Marcos. I guess thank you again, Darek, for the presentation.
Well, thanks for watching, and
Yeah, it was nice. And I will write an email again